straightforward, but turns out to be wonderfully weird. Quantum spin.
Uh-huh.
Now, forget the image you might have of tiny particles actually spinning like little tops. That's really not what we're talking about here.
No, absolutely not. It's something much more fundamental. What we're diving into today is this intrinsic form of angular momentum.
Intrinsic.
Yeah, it's as fundamental to a particle as its charge or its mass. Think of it more like a fundamental label. It dictates how a particle interacts. Quantum spin, in essence, is a particle's inherent quantum identity in terms of its angular behavior.
Exactly. And this isn't just some isolated quirk, right? Something happening way down at the subatomic level.
Not at all.
Our sources for this deep dive show us how this concept of quantum spin just ripples outwards. It influences everything. Individual particles, sure, but also the structure of atoms, molecules, even driving some really cutting-edge technologies. It's kind of amazing how this tiny non-classical property has such huge effects.
That's right. And we've got material covering, the real foundations of spin, how it dictates the architecture of atoms, and magnetism, too.
Magnetism, right.
And its essential role in the very bonds holding molecules together, not to mention its part in emerging fields.
So our mission here is really to pull out the core insights about this quantum property and show you just how, surprisingly significant it is.
Exactly. Why it matters.
So let's get down to it. What exactly is quantum spin? We've said what it isn't. It's not physical rotation.
Right. Crucial point.
But what is the key idea? Our sources keep calling it fundamental.
Okay, so the crucial thing to grasp is that spin is an intrinsic form of angular momentum. It's built in.
Built in, okay.
Every particle has a specific fixed amount of this internal angular momentum. We describe it with the spin quantum number is nullis.
Got it.
Now, this number isn't just any value, it's quantized.
Quantized meaning discrete values,
Yeah.
like steps.
Exactly, like steps, yeah. Not a smooth ramp, you can only have specific amounts. So for bosons, like photons, S is a whole number 0,
Right.
1, 2. Okay.
But for fermions, the particles that make up matter, like electrons, protons, S is a half integer, so 12, 32, 52, and so on.
Okay, so different particle types have different built-in spin amounts. And our sources really focus on electrons as the key example, right, with spin 12.
Precisely. The electron is sort of the classic fermion, SS12. And here's where it gets really interesting. The direction of this spin is also quantized.
The direction, too?
Yep. When we measure the spin along a certain axis, let's say the z-axis, it can only point in specific ways.
Yeah.
These are defined by another quantum number, Ms, the spin magnetic quantum number.
Okay.
For an electron with SS12, there are only two possibilities for Ms. It's either plus 12.
Which we call spin up.
Right, spin up.
Yeah.
Or it's ME's Kaczynskis 12.
Spin down.
Spin down, that's it. Just those two. So S is like the fixed size or magnitude of the spin for an electron, and Ms tells us which way it's pointing, up or down, when we measure it.
So even though it isn't physically spinning, it acts like it has this internal angular momentum, fixed amounts, specific directions. Exactly.
And because the electron is charged, this spin has another big consequence, doesn't it?
Yeah.
Makes it magnetic.
Yes, that's absolutely key. The spinning charge, the quantum property acting like spinning charge creates a tiny magnetic dipole moment.
Like a tiny bar magnet.
Precisely. A little north and south pole. It's this inherent magnetic property of individual electrons that ultimately scales up to give us the magnetism we see in everyday life.
Wow. From tiny electron magnets to, like, sticky notes on the fridge.
Pretty much. Or even the Earth's magnetic field, fundamentally. It all starts there.
Now, this spin property, this up or down thing, it leads to some really strict rules about how electrons behave together. Our sources really hammer home the Pauli exclusion principle. Why is this one so important?
Pauli. Yeah, it's fundamental. The principle states that no two identical fermions can occupy the same quantum state simultaneously.
Identical fermions.
Yeah.
Like two electrons.
Exactly. They can't be in the exact same quantum address at the same time. Think of it like seats on a bus. If you have identical twins, they can't sit in the exact same seat, defined in every way.
Okay.
So for electrons and atoms, if two electrons are in the same atomic orbital, which means they have the same energy level, same orbital shape, described by other quantum numbers,
Right.
then their spin magnetic quantum numbers, their M's values, must be different.
One has to be spin up, the other spin down.
It has to be. They're excluded from having the same spin state if everything else is identical.
So this one up, one down pairing in an orbital isn't just, like, convenient. It's a fundamental law.
Absolutely. A direct consequence of the Pauli principle.
And our sources say this is basically the foundation for, well, the entire periodic table. That seems huge.
It is huge. The Pauli exclusion principle dictates how electrons fill up the available energy levels and orbitals in an atom. That determines the atom's electronic configuration.
Which determines its chemistry.
Exactly. Its chemical properties. Why sodium is different from chlorine, why noble gases are inert. It's why atoms don't just collapse with all electrons piling into the lowest energy state. Spin, through the Pauli principle, is the architect. It gives each element its unique identity.
Fascinating. Wow. Okay, so that's individual electrons and their rules. What about the whole atom? Does an atom have an overall spin?
Yes, it does, but it's a bit more complex. The total angular momentum of an atom comes from a combination of things.
Okay, like what?
Well, you've got the spins of all the individual electrons added up somehow. Then you've got their orbital angular momenta that's from them moving around the nucleus.
Right, electrons orbiting.
And then there's also the spin of the nucleus itself, though nuclear spin effects are usually much smaller, magnetically speaking.
So it's electron spins, electron orbits, and the nucleus all contributing.
Yeah, and they all couple together, interact in pretty intricate ways. Our sources mention things like LS coupling and JJ coupling.
Okay, don't need to go super deep there, maybe.
No, probably not for this overview, but they're just different models physicists use to describe how these angular momenta combine, like different ways of doing the quantum accounting. It depends on the atom.
So it's a team effort for the atom's total angular momentum.
Yeah.
What happens in atoms where the electron shells are completely full?
Yeah.
Like the noble gases.
Good question. In atoms or ions with completely filled shells and subshells, things tend to cancel out beautifully.
Cancel out.
Yeah. You have equal numbers of spin-up and spin-down electrons paired in every orbital, so the total electron spin adds up to 0. And often the orbital angular momenta also cancel out.
So no net spin, no net orbital momentum means no net magnetism.
Pretty much. These atoms or ions are generally diamagnetic. They actually weakly repel an external magnetic field. All the little internal magnets are perfectly balanced, canceling each other out.
Okay, so filled shells, paired electrons, diamagnetic. Makes sense. But what about atoms with, leftover unpaired electrons?
That's where it gets interesting magnetically. If an atom has one or more unpaired electrons, there's a net electron spin angular momentum. The spins don't all cancel.
And that makes the atom
paramagnetic. It's weakly attracted to a magnetic field because it has this net magnetic moment from the unpaired electron spins.
Okay.
And in solids, if these unpaired spins on different atoms line up in organized ways, you can get much stronger forms of magnetism. Ferromagnetism, like your permanent magnet,
Right.
or antiferromagnetism, where they line up alternating up and down. It all comes down to those unpaired electron spins.
And there are rules for how they prefer to line up within an atom, too,
Yeah.
right? Hund's rules.
Exactly. Hund's rules guide this. Hund's first rule particularly is key here. It says that within a subshell, with multiple orbitals of the same energy degenerate orbitals,
Okay.
electrons will fill each orbital singly first before any orbital gets a second electron. And importantly, these singly occupied orbitals will have electrons with parallel spins.
So they all point the same way, up or down.
Yeah. Yep. Maximize the total spin. This actually lowers the energy of the atom. It's like the electrons prefer their own space and want their spins aligned if they can, before being forced to pair up.
Kind of like people on a bus again, taking empty double seats before sitting next to someone.
Sort of, yeah. And wanting to face the same direction if they're in adjacent seats. It minimizes repulsion in a quantum mechanical way. Hund's rule governs this preference and is crucial for predicting atomic magnetism.
Okay, maximizing spin multiplicity for lower energy. Got it.
Yeah.
Now, let's scale up again, from atoms to molecules. How does electron spin play into chemical bonding? It seems like it must be important.
Oh, absolutely central. You can't really understand chemical bonds without spin. Think about the most common type, the covalent bond.
Sharing electrons.
Right, two atoms share a pair of electrons. Now, molecular orbital theory tells us these two shared electrons occupy a bonding orbital. And here comes Pauli again.
The exclusion principle.
Yep. Those two electrons in the same bonding orbital must have opposite spins. One up, one down. They cannot have the same full quantum state, and since they're in the same orbital, their spins must differ.
So that spin pairing, that up-down requirement, is what actually allows the bond to form.
It's fundamental to it. That pairing allows the electrons to coexist in that shared space and creates the attractive force holding the atoms together. It's like the quantum handshake forming the bond.
And this pairing results in a net spin of 0 for that bond pair, right?
Yeah.
Our sources called it a singlet state.
Exactly. The antiparallel spins, plus 12 and negative 12, add up to a total spin S of 0. That's a singlet state. This spin pairing is a major factor in the stability of most chemical bonds.
Okay, so spin pairing holds molecules together. But within molecules, there are more subtle spin interactions too. Sources mention exchange interaction, dipole-dipole.
Yes, things get even more nuanced. The exchange interaction is purely quantum mechanical. It arises because electrons are indistinguishable particles.
Indistinguishable.
Okay. It's a bit weird, but it effectively creates an interaction whose sign depends on whether the electron spins are parallel or antiparallel. We already saw its effect in Hund's rule.
Favoring parallel spins.
Right. It favors parallel spins in different orbitals because that configuration keeps the electrons, on average, further apart, reducing their electrostatic repulsion. In molecules, this exchange interaction is key to the energy difference between singlet spins paired, SCO0, and triplet spins parallel, S1 states.
Okay, and dipole-dipole.
That's more straightforward conceptually. It's just the direct magnetic interaction between the magnetic moments of the two electron spins, like two tiny bar magnets interacting.
Weaker.
Generally weaker than the exchange interaction, yes, but it's still relevant, especially in techniques like electron spin resonance or ESR.
Okay, you mentioned singlet and triplet states. Let's clarify those again for molecules.
Sure. So if you have a system with two important electrons, like in a bond, or maybe two unpaired electrons, a singlet state is when their spins are antiparallel, paired up, total spin S, 0. There's only one way for that to happen.
S is 0, singlet.
Got it. A triplet state is when their spins are parallel, both effectively up, or however you want to think about it. The total spin quantum number S equals 1. And because spin is a vector, an S1 state can actually orient in 3 different ways in a magnetic field, hence triplet.
S1, 3 ways, triplet.
Okay.
And most stable molecules are?
Most stable, closed-shell organic molecules have a singlet ground state. All electrons are paired up in orbitals.
But triplet states exist.
Oh, yes. They're often found as excited states of molecules. If you pump energy in, you might flip a spin. Or they are the ground state for molecules that naturally have unpaired electrons, like molecular oxygen, O2, or radicals.
And Hund's rule comes back here too, preferring the triplet state if electrons are in different orbitals.
Exactly. If you have 2 electrons in different degenerate orbitals, the triplet state, parallel spins, is generally lower in energy than the corresponding singlet state, antiparallel spins, thanks to that exchange interaction reducing electron repulsion.
Okay, we've talked electron-electron. But what about electron-nucleus interactions? The sources mentioned hyperfine interactions. Sounds small.
They are small, energetically speaking, but incredibly informative. Hyperfine interaction is the coupling, the interaction between an electron spin magnetic moment and the magnetic moment of a nearby atomic nucleus.
If the nucleus has a magnetic moment, right? Not all do.
Correct. The nucleus itself needs to have spin. Many isotopes do, like hydrogen-1, carbon-13, nitrogen-14.
Okay.
This interaction, though weak, causes tiny shifts or splittings in the electron's energy levels that depend on the nuclear spin state.
And this is useful how?
It's the absolute key to electron paramagnetic resonance, EPR or ESR spectroscopy. By measuring these tiny hyperfine splittings, you can figure out which nuclei the unpaired electron is interacting with, how close it is, and get really detailed info about the electron's environment in a molecule or material.
So it's a probe.
Right.
Very cool. Which brings us neatly to the payoff, really. The implications and applications. Spin isn't just theory. It's out there doing stuff.
Absolutely. It's everywhere. We already touched on magnetism.
Right. All magnetism basically boils down to electron spin alignments.
Fundamentally, yes. From diamagnetism in things with paired electrons to paramagnetism from unpaired spins, all the way to the strong ferromagnetism in iron, it's all about how electron spins behave and interact collectively.
And spectroscopy. We mentioned ESRPR.
Definitely ESRPR for directly studying unpaired electron spins. Think free radicals in chemistry or biology, transition metal ions in catalysts, defects in semiconductors. It's crucial.
What about NMR? That's nuclear spin, right?
It is based on nuclear spin, yes.
Uh-huh.
But the chemical environment that NMR probes, the magnetic field felt by a nucleus, is heavily shielded or deshielded by the surrounding electron cloud. And the distribution of that electron cloud is dictated by chemical bonding.
Which depends on electron spin pairing.
Exactly. So electron spin has an indirect but vital influence on what we see at NMR as well.
Okay. And chemical reactivity, does the spin state matter there?
Yeah. Hugely. Take oxygen, O2. As we said, its ground state is a triplet. It has two unpaired electrons with parallel spins.
Right.
This spin state makes it react differently than if it were a singlet. Many reactions involving O2 proceed via radical pathways because of its triplet nature. Also, there are spin conservation rules in reactions. The total spin often needs to be conserved, which can make some reactions forbidden or slow if they require a spin flip.
So the spin state can actually control whether a reaction happens easily or not.
It can be a major factor, yes.
And then the really futuristic stuff, quantum computing and spintronics. Spin is central there, isn't it?
Absolutely. For quantum computing, the two states of an electron spin up and spin down make a natural candidate for a quantum bit or a qubit.
The 0 and 1 of the quantum world.
Exactly. And because it's a quantum system, it can be in a superposition of both up and down simultaneously, and qubits can be entangled. That's where the potential power of quantum computing comes from. Electron spin is one of the leading platforms researchers are developing for qubits. Nuclear spins, too, sometimes.
And spintronics. Sounds like spin electronics.
That's the idea.
Yes.
Traditional electronics just uses the charge of the electron to carry information. Spintronics aims to also use the electron's spin degree of freedom.
So using both charge and spin.
Right. The hope is to create new devices, memory, sensors, logic gates that are potentially faster, smaller, and use less energy by manipulating electron spin. It's a really active research area. Think things like MRAM memory, spin transistors.
It's just incredible, really, thinking back over all this fundamental property, quantum spin, which isn't even real spinning. It dictates how electrons pair up, how atoms are built, why magnets work, how molecules bond, how reactions happen, and now it might be the key to next-generation computing and electronics.
It truly is amazing. It's one of those core quantum ideas whose consequences just cascade outwards into almost everything we see and do, from the structure of matter to the technologies of the future.
Yeah, this deep dive really highlights how that seemingly abstract quantum world is just completely intertwined with our macroscopic reality.
Couldn't have said it better myself. It's fundamental.
So as you, our listener, think about all this, maybe consider the sheer impact of this one. Kind of bizarre. Quantum property, spin. It really makes you wonder, doesn't it? What other hidden quantum rules might be lurking out there? Properties we haven't maybe fully grasped yet that could have equally profound consequences for how we understand the universe and what we can do with it technologically.
Yeah.
How deep do the connections between the quantum and the classical really go? Definitely something to ponder.